Section 7.8 is on improper integrals. Now, recall, we can interpret a definite integral as the area of a region. And so far, all of those regions that we've looked at, they've had a finite width and a finite height. So what makes an integral improper is when either the width of the interval is infinite, or somewhere in between the two endpoints, there's a place where the height is infinite. So we break those up into type 1 and type 2. Type 1s are the kinds where you have an infinite width, and either one of your endpoints is infinity or negative infinity, or maybe you've got both of them on there. And the type 2s are integrals where you've got from a to b, where a and b are just plain numbers, but your function here, f of x, has a vertical asymptote somewhere between a and b. So let's go ahead and look at the type 1s. First up, I want to look at one very particular type of integral. Integrals like this, where you're integrating from a to infinity of 1 over x to the n dx. These turn out to be infinite whenever n is less than or equal to 1, and they're finite when n is greater than 1. Now, I want to look at Desmos to kind of give you the sort of a visual of why that's true, and then we're going to work through a few examples. One here where n is bigger than 1, one where n is equal to 1, and there's a 3 on the front of it, and then one here where n is less than 1, n's 1/2. But first up, let's just look at this integral on Desmos. So there's a link here. If you look at the PDF, that should be a clickable link for this Desmos sheet. Let me make Desmos bigger. All right, so here we've got f of x. Our f of x function here is 1 over x to the n, and I'm shading in the area that this integral here, 1 to, now really it should be 1 to infinity, but instead of putting in infinity, I'm just putting in a large number, 999. And we're going to integrate this from 1 to that big number, and I want to see what happens here. Now, when x is bigger than 1, notice what happens here. This thing shrinks down really, really fast. This is 1 over x to the 10th that we're looking at. But if I bring this back down, notice it stays where the y value of this function, 1 over x to the n, just drops off to nothing really quickly. And it drops off fast enough to make this area here finite. But if I move this back closer to 1, notice it gets bigger and bigger. But something is going to fundamentally change here. Let me zoom out a bit. When I get back here, when I hit 1, things get bigger. Or the sort of the thickness of this area gets bigger. And 1 is a place, it's actually called a bifurcation point where things change qualitatively. When we get to 1, the area becomes infinite. Now it's not easy to see here because again, I'm not integrating the entire thing. I'm only integrating from 1 to 999. But if I make this get bigger and bigger, notice how that number gets bigger and bigger. If I come back and I change this to say 2, no matter how big I make this number, that's going to converge to 2. Okay, it says undefined, but that's Desmos running into problems. Notice that right there, it's getting really close to 2. Or I'm sorry, get really close to 1. If I pull up here to 3, as my as n goes to infinity, or not n, as my b goes to infinity, this is getting closer and closer to 1/2. But if you come back here to 1, making this number bigger makes this grow arbitrarily large, and back here, the same sort of thing happens. So anyway, a difference happens when n passes across 1. Now, let's look at why that's true. So let's look at these examples. Basically, the three examples I've got here are, this one has n equals 3. So according to this up here, if n is greater than 1, the area is going to be finite. Now, if the area is less than or equal to 1, the area is going to be infinite. And that's what happens here, because n is 1. And here n is 1/2. So this one is also going to be infinite. But don't take my word for it. Let's work these out and see what happens. All right. So for example 101, let's see. We'll just integrate this like normal. This is integral from 1 to infinity of x to the minus 3. When you add 1 to that, you get x to the minus 2, and then divide by -2. We're going from 1 to infinity. So this is going to be minus 1 over 2x squared from 1 to infinity. All right, now what I'm supposed to do here is, if I want to be formal about this, I need to write this as a limit. Limit as t goes to infinity of -1 over 2t, or 2x squared from 1 to t. So basically I'm replacing the infinity with t, and I'm taking the limit as t goes to infinity. So when I do that, then I get limit as t goes to infinity of 1 over, let's see, it's -1 over 2t squared. And then when you plug in the 1, you get -1 over 2 times 1 squared. And notice what happens here. This guy, when t goes to infinity, you get -1 over infinity, which is 0. And then this one gives you plus 1/2. So the answer here is 1/2. And we saw that a minute ago on Desmos. Because on Desmos, when we took this and we looked at what happens when n is exactly 3, then this is converging to 1/2. And that's sort of the long formal way of doing it. Which formal way is good. But you can also do this informally. And informally, what I'm going to let you do here is just plug in the infinity. Informally, think of 1 over infinity equals 0. That's not formal, it's not rigorous, but it gets the job done. If we take this now and plug in our endpoints, we get -1 over 2 times infinity squared minus -1 over 2 times 1 squared. And of course, this gives you 0 plus 1/2, which is 1/2. All right, let's look at the next one. Really, sort of the key here that makes this finite is the fact that when we do this integral, the x squared, or the whatever power of x that we get, winds up staying in the denominator. So the thing, when t goes to infinity, it makes the denominator grow large and it gives you a 0. Now this problem here, first up, I would move the 1/3 out front, get 1 over x dx, still from 1 to infinity. And if we integrate 1 over x, we get ln x from 1 to infinity. And then we can plug in our endpoints. We get 1/3 ln of infinity minus 1/3 ln of x, or no, of 1. But this guy right here, this goes to infinity. And again, what I'm doing there by saying natural log of infinity is I'm saying what happens to the natural log function when the argument you put in grows large. Well, natural log, it looks like this. And it grows slowly, but it does keep growing up, so it goes to infinity. So we've got infinity minus a third, so that is infinity. And the word we have for this is divergent. The integral is divergent because it goes to infinity. All right, now let's look at this last example. N is 1/2 here, so I'm going to integrate it like this. I'll write this as x to the minus 1/2 dx. And when I integrate that, I get x to the positive 1/2, and then I have to divide by that, so multiply by 2 from 1 to infinity. So we've got 2 root x from 1 to infinity. Now technically, I'm gonna do this one informally. We get 2 root infinity minus 2 root 1. You know, if we did this formally, instead of just writing this out, we'd write this as a limit, as the thing under here goes to infinity. So in other words, what we get here is infinity minus 2, which is just infinity. So this one also diverges, which means the area underneath is infinite. And notice what's happening. The 2 that became infinite, it happened because the x, you know, the thing that's going to infinity, the x in this case moved up to the numerator. So we've got the numerator going to infinity, and that makes it infinite. Same thing happened here. The x, it moved to the numerator inside of a natural log. But up here, when this was when this was bigger than 1, then we get this, and after we integrate, the x stays in the denominator. And so that makes this, it makes the limit part go to 0, and we get something finite. So anyway, that's 3 examples of those.